All right, let's talk about something you've probably seen a million times, a globe. You know all those lines crisscrossing over it? Well, they are way more than just decoration. They're actually a code. And today, we're going to crack it. Let's get into it.
Seriously, have you ever really stopped to wonder what they're for? It's so easy to just kind of gloss over them, right? But those lines, they are the secret language of our planet. And by the time we're done here, you are going to be fluent.
So, first things first, let's talk about the globe itself. It is so much more than just a cool looking ball for your desk, right? It's a true model of the Earth. I mean, it's our planet in miniature, showing everything continents, oceans, countries in their correct shape and size. It's honestly the most accurate way to see the world as it really is. Okay, so before we start drawing all these imaginary lines all over it, we've got to understand the canvas we're working with. And our canvas, the Earth, has a kind of funny little secret about its shape. Get this, the Earth is not a perfect sphere. Nope, it's actually a little bit flattened at the top and bottom, at the poles, and it kind of bulges out a bit in the middle, around the equator. It's a subtle difference, but believe me, it's a super important detail that affects, well, pretty much everything. All right, time to start drawing our lines. The first set we're going to look at are the horizontal ones. Just picture them wrapping around the globe like hula hoops. These are called the parallels of latitude.
Yeah, think of them like these flat circles that are always parallel to each other. They never, ever touch. And they're all parallel to the big one, the most famous one of all, the equator. Their whole job is just to tell you how far north or south of the equator a place is. Simple as that.
Okay, now take a look at this. This right here is basically our roadmap, because out of all those latitude lines, there are 5 that are really important, and I mean crucial. They're not just some random lines on a map. Each one marks a major boundary that defines our world's geography and, get ready for it, its climate.
So let's meet the key players. Right in the middle, we've got the equator. That's our 0 degrees starting point. Then, heading north, you hit the Tropic of Cancer at 23.5 degrees north. And heading south, you've got its mirror image, the Tropic of Capricorn at 23.5 degrees south. Go even further out and you get the Arctic and Antarctic circles, both at 66.5 degrees. Definitely try to remember these names and numbers because they're going to come up again in a big way.
But here's the thing. Knowing how far north or south you are, well, that's only half the puzzle. To find an exact spot, you need another set of lines. This time, we're talking about the ones that run from top to bottom. And these are called the meridians of longitude. Now, unlike our latitude hula hoops, these guys are not parallel at all. In fact, they all meet up at the north and south poles. A really good way to picture it is like the slices of an orange, right? They all come together at the top and the bottom.
So, if they all meet up, you might be asking, well, where do we start counting from? It's a great question. A long time ago, everyone agreed that the starting line, the 0-degree line for longitude, would be the prime meridian. And this line runs right through a place in Greenwich, England. So every other longitude line is measured as being either east or west of that one specific spot. All right, let's do a quick side-by-side comparison. Latitudes run east-west, and they're always parallel. Longitudes run north-south, and they all meet up at the poles. And here's another huge difference to remember. You've only got 180 degrees of latitude, but for longitude, you need a full 360 degrees to go all the way around the world.
So, we've got our horizontal lines, our latitudes. We've got our vertical lines, our longitudes. Now let's see what happens when we put them together. We create the global grid. And this, my friends, is where the real magic happens. You might be thinking, okay, but why do we really need both? Couldn't we just get by with one set of them? And that's a totally fair question. The answer, as it turns out, is actually pretty straightforward. Okay, here is the whole reason why. I want you to picture this. You've got the Tonga Islands out in the Pacific Ocean, and then you have the Mauritius Islands, way over in the Indian Ocean. Believe it or not, they are both on the exact same latitude, 20 degrees south. So they're on the same horizontal street, if you will. But they are thousands of miles apart. If you only had latitude, you wouldn't even know which ocean you were in. You need that second coordinate, the longitude, to pinpoint the exact spot. And this is how it all works in the real world. That grid of intersecting lines gives every single spot on the planet its own unique address. A place like Dhubri in India is at 26 degrees north, 90 degrees east. That's its address. And there is nowhere else on Earth that has that exact same combination. It is totally unique.
Okay, so this is awesome. We can now find any point on the map, but it gets even better. Because this very same system of lines, it's the key to unlocking the final piece of the puzzle, climate. It helps us understand why some parts of the world are boiling hot, why some are freezing cold, and why some are, well, just right.
I know that might sound a little weird, right? I mean, how can these imaginary lines we've just been talking about have anything to do with the actual temperature outside your window? But they do. They are totally connected, and it all boils down to one single thing: the sun.
Hey, look at that. It's our old friend, the latitude map. We're back to it, but this time we're going to look at it completely differently. Because it turns out these lines do more than just measure distance. They actually draw the boundaries for our planet's climate zones. And it's all about the angle of the sun's rays. The more directly the sun hits a spot, the hotter it's going to be. And that simple fact, the angle of the sun, creates three main heat zones across the globe. You've got the torrid zone, the temperate zones, and the frigid zones. Let's break down what each of those means. Okay, so check this out. First up is the torrid zone. This is the area sandwiched between the Tropic of Cancer and the Tropic of Capricorn. It gets the most direct hit from the sun, so it gets the maximum heat, super hot. Next, you have the temperate zones. These are the areas between the tropics and the Arctic and Antarctic circles. The climate here is moderate, not crazy hot, not crazy cold. And finally, you have the frigid zones, way up near the North Pole and way down near the South Pole. The sun's rays hit these areas at a really sharp angle, so they get the least heat and are, you guessed it, very, very cold. And this right here really explains why the torrid zone is the hottest. It says the midday sun is exactly overhead at least once a year in this whole area. Think about that. The sun is literally straight up, beaming down with maximum power. That's why that zone gets the most intense heat. So that kind of brings it all full circle, right back to you. You now know the secret. You have the tools to look at a globe and not just see a bunch of lines, but to see the code. A code that tells you where a place is, and even what it feels like to be there. So the next time you see a
starting line. Because before they agreed, it was pure chaos. I mean, can you imagine? A map made in France used a zero line that ran through Paris. A British map used one that ran through London. As the world got smaller with railways and global shipping, this wasn't just confusing, it was genuinely dangerous and really bad for business.
Now, people had been trying to solve this for ages. Even the ancient Greeks gave it a shot. But by the late 1800s, with a rapidly connecting world, things hit a breaking point. We couldn't wait any longer. So, in 1884, a bunch of countries sent delegates to Washington, D.C. for one reason and one reason only: to vote on a single prime meridian for the whole planet.
So, why Greenwich, a neighborhood in London? Well, it wasn't a random pick. The decision basically came down to pure pragmatism. At that time, a staggering 72% of the entire world's shipping already used sea charts that were based on Greenwich being the 0-degree line. Choosing it was just the path of least resistance. It would help the most people right away.
And just like that, it was settled. This spot, the Royal Observatory at Greenwich, became the official starting line for the world. Longitude 0 degrees. From here, we measure 180 degrees to the east and 180 degrees to the west. But wait, the story actually has a pretty cool modern twist. Okay, I want you to just look at this number for a second. 102.478 meters. What on earth could that possibly be referring to?
Well, get this. You know that famous brass line at Greenwich where all the tourists take pictures with one foot in the eastern hemisphere and one in the west? Yeah, that's not actually the prime meridian anymore. Not to your phone, anyway. Our modern satellite systems are so precise, the actual scientifically true prime meridian is about 102 meters east of that old line. That's basically the length of a soccer field. The real zero line your phone uses is just kind of floating in a nearby park. So this grid did an amazing job of helping us figure out where we are. But it turns out, in solving that problem, we also accidentally found the perfect tool to standardize something that was just as messy: time itself. It makes perfect sense when you think about it, right? As the Earth spins on its axis, different lines of longitude face the sun. The people at that 1884 conference figured this out and used it to create our modern system of 24 time zones. They basically just sliced the globe into 24 segments, like an orange, with each slice being about 15 degrees of longitude wide.
And the math behind it is just so simple and elegant. The Earth turns a full circle,
360 degrees in about 24 hours. So you divide 360 by 24, and you get 15. Boom! That means every hour, the Earth spins 15 degrees. So for every 15-degree slice of longitude you cross, the local time changes by 1 hour. Simple as that.
Before this system, you had what was called local time. Every single town just set its clock by whenever the sun was highest in its own sky. So it could be noon in one town and 12:05 in the next town over. Can you imagine trying to create a train schedule in that world? Standard time, all based on longitude, finally brought some order to all our clocks.
So from helping ancient sailors navigate the seas, to coordinating our train schedules, to guiding the GPS in your phone today, this completely